Hey guys, welcome back. So this is week 7, and I'm going to be talking about binary search trees today. And so yeah, let's just hop into it. So the first question may be, what is a BST? And in order to understand this, we need to first understand what even a tree is. And so the two rules for trees essentially consist of a set of nodes and then a set of edges that connect those nodes. And there's exactly one path between any nodes. So just to make this a little easier, because I know it's sometimes hard to understand just like definitions that are originally given to you, we can kind of go through some examples. So this, for example, this single node would be considered a tree. Similarly, if I had something like this would also look like a tree. And I could even do this. And this would be a tree. So yeah. However, if I had something like this would actually not be considered a tree anymore, because I don't fulfill this exactly one path between any nodes. Alternatively, if I had something like this would also not be a tree. And so yeah, hopefully that makes a little bit of sense on like what a tree is and stuff like that. And then I guess one more example. So yeah, we can just kind of hop into the problem now. And also something like this, another good example. So this would also be not considered a path, because it, again, would not fill that exactly one path between any nodes. Because if I wanted to get, say, start to end, I could either go this way, or I could go this way, and we can see that's two paths. So yeah, now let's get a little bit more specific. And so what exactly is a binary search tree? And a binary tree is merely a tree with each non-leaf node having two children. A binary search tree, on the other hand, is a binary tree where the left child is smaller than the root. The right child is larger than the root, and both children are binary BSTs. And then finding a BST gives us order array. That's another important feature to know. So, for example, this is a binary tree, and we can see here that it's not sorted because we know it's not a BST, because 2 is greater than 1. And we can see that in this case, this is not a BST. So this tree is not a BST. However, this is a BST because this value, the left-hand value, is less than the root. So 1 is less than 2. And the right-hand value is greater than the root. So it's less than 3. So yeah, we can see that how that's a BST. And then the next question may be like, why are BSTs so useful? Like what can we do with BSTs? And the most useful thing I would say, and like the most practical thing, is finding items in log n time. And the reason we can do this is we can kind of abide by these rules. So let's take this for example. So let's say we want to find 5. So we start at the root. We'd say, okay, if search item is less than t.val, go left. So we're trying to find 5. Okay, well, yeah, it looks like the search item is indeed less than t.val, because we know that the t.val in this case for the root would be equal to 6, and we know 5 is less than 6. So we're going to go left. So we get to this 4, and we say, okay, if search item is less than t.val, we know that 4 is not less than 5. Or sorry, I'm sorry, 5 is not less than 4. So we can't do this condition. So we go to this next condition right here. And then we say search item greater than t.val. We do know 5 is greater than 4. 5 greater than 4. So we'll go right. And then lastly, we see that we're at 5. So we go through these conditions, and then we see that we're at 5, and then we return 5. And the reason this is so powerful is because there's no need to go through every single node in the tree. We can instead just go through them like this, and it's a much more efficient way to find nodes and much faster in the runtime. So yeah, hopefully all this makes sense. And Ronald's going to walk you guys through question 2 and 3. And have a great week.